Okay, so what was your question?
How to do number 54 on section 2-1.
2-1?
Yes, sir.
$54 on 2-1. So this is 2.1 or 54. Given alpha and beta complementary, verify the following equations. So alpha and beta are complementary. Okay, that's an assumption. Furthermore, we have to verify this identity, sine squared alpha tangent squared beta. Minus cosine squared beta is equal to 1. Okay. So we start off on the left-hand side and we show the right-hand side is equal to 1. Okay. Now, we utilize the fact that alpha and beta are complementary. What does alpha and beta complementary imply?
That alpha equals 90 minus beta.
Yeah, that alpha plus beta sum to equal 90 degrees. So what you said is a implication of that. You said that the alpha is equal to 90 degrees minus beta. That can definitely be utilized. And it's a good idea to utilize that because we can use cofunction identities. Okay? Well, let's see if that very one helps. So that means I get sine squared of 90 degrees minus beta, tangent squared beta minus cosine squared beta. But what is this equal to? Remember the cofunction identities? Is that, for example, sine of beta, for example, is equal to cosine of 90 degrees minus beta. Also, that cosine of beta is equal to sine of 90 degrees minus beta. So any of these work. So if I have sine squared of 90 degrees minus beta, that can actually decompose to cosine squared beta, right?
Sir.
Okay. So then moving the calculation over here, I get, what is tangent? What is tangent squared beta?
Sine squared beta over square beta.
Yes. And I'll just rewrite this. Right. So then we notice that the cosine betas cancel out. So now we have sine squared beta minus cosine squared beta. This is supposed to end up equaling 1. Can we set it equal to 1 yet?
Mm-hmm.
No.
No.
No, you can't, right? If this was a plus, you could,
Yeah.
but it's not. So what do we do?
The plot, no, it's, I think, do you break it to sine beta plus cosine beta times sine beta plus cosine beta? No?
Mm-mm. Mm-mm. So what could have gone wrong is us deciding to switch alpha for this 90 minus beta. Would it matter if we decided to change beta for 90 minus alpha? Would that help at all? You get what I'm saying?
Kind of.
I'm saying, instead of trying this route here, we tried to change alpha to beta. Why not try to change beta in terms of alpha? So meaning, if this is true, we can also say that, well, at the same time, beta is equal to 90 minus alpha. So that we could convert these to (90 minus alpha). So now what? Well, again, it's a cofunction identity. So tangent of, let's say, alpha is the same thing as cotangent of 90 degrees minus alpha. Similarly, cotangent of alpha is the same thing as tangent of 90 degrees minus alpha. 90 degrees minus alpha. So that means cotangent squared is what this is. So we can rewrite that as sine squared alpha cotangent squared alpha minus this cosine squared 90 minus alpha. Recall, sine of alpha is the same thing as cosine of 90 degrees minus alpha. So that means when I see a 90 degrees minus alpha, that's the same thing as a sine squared alpha. Does this help at all? Notice that this becomes sine squared alpha times cosine squared alpha over sine squared alpha minus the sine squared alpha. But notice you're in the same predicament. You have a cosine squared alpha minus sine squared alpha. We want that to equal 1. This was what we were trying to prove. Does that equal 1? No, it doesn't. Doesn't equal 1. So we tried utilizing this, and it still isn't working. We tried doing it for beta. We tried doing it for alpha. What else is it that we can do? Going back here, because we're clearly hitting a dead end here. We have the Pythagorean identity cosine squared alpha plus sine squared alpha is equal to 1, right? But it has to say plus, not minus, the way we have it. Furthermore, if you wanted to somehow solve for cosine squared alpha, you'd get that. But if I plug this in here, I get 1 minus sine squared alpha minus sine squared alpha. But this is equal to 1 minus 2 sine squared alpha. Still, it doesn't equal 1. So then you might think, well, maybe I should factor out a sine squared alpha. Will that help? So you get this is a cotangent squared alpha minus a 1. Is what's in that parentheses ring the bell? Does that ring a bell?
No.
You remember the identity? What is it in section 2.1? One of the Pythagorean identities involving cotangent. Was that in this section? It was what? Okay, so 1.4. Let's go back a little bit more. What's that one that involves cotangent? Oh, we have 1 plus cotangent squared theta is equal to cosecant squared theta. And we'll just call it alpha. Okay, but we have 1 minus, or we have a, cotangent squared minus 1. So what's going on here? How can I relate what's in here to what's over here? To get,
Can you move 1 over? No.
yeah, you can, but then you get cotangent squared alpha is equal to cosecant squared alpha minus 1. So you can replace that with cosecant squared alpha minus 1. So then this becomes sine squared alpha times, we're replacing cotangent squared alpha with cosecant squared alpha minus 1. So this becomes minus a 2. But it's supposed to equal 1. What is cosecant squared alpha? So this is what you get. But still, if I distribute the sine squared alpha, then I get 1 minus 2 sine squared alpha. It's supposed to equal 1. Any ideas? We tried cofunction identities. We tried trig identities for the Pythagorean theorem. Any ideas? This is number 54 on 2.1. You're trying to show that this is true, assuming that A and B are complementary. Maybe it's not true. Anybody have any suggestions? alpha and beta are complementary means, right?
Yes.
So solving for alpha again. I'm trying to guide you guys to the solution yourself. So alpha is 90 degrees minus beta by hypothesis, right? So get this equation. Right? Then replace every alpha. We tried this already. Did it work? So we can get everything in terms of beta. So this becomes but this is the same thing as so these cancel, and again you're left with does that equal 1? So maybe that gentleman over there is correct. Maybe it isn't an identity. Okay, I'm gonna leave this up here. It's gonna be up in the air. If anybody has an idea, you let me know. When is this due? Thursday, okay. Let me know on Thursday if you figured it out. I have to move on to 2.2. But I would say the hint is to use the cofunction identities. Solving right triangles, 2.2. Okay, before at the beginning of class, I'm more than willing to do some homework problems. But yeah, I'm gonna need you guys to help me out on there. Okay. So now let's do a problem where we want to solve a right triangle here. Let's get let's say this is 17.9 over here. And this is C. We don't know it yet. And let's say this is B. And this is 30, which implies this must be 60. So what is C and what is B is what we want to know. How do we find C and how do we find B? Any ideas?
H will proceed to hypotenuse, square root, x squared, y squared.
Say what? Say what? It's 30.
No, we can do the sine of 30 degrees almost B.
Oh, the sine of 30. So what is the sine of 30?
1/2.
No, not always.
opposite.
It is always opposite over hypotenuse. It just so happens when you have a right triangle and your hypotenuse is equal to 1, you get what that young man said. Would you say 1/2?
Yes, sir.
Yeah, that's only true if you have a 30, 60, 90 triangle and your hypotenuse is equal to 1. That's when you get 1/2. In general, you don't get 1/2. So now that we set up this equation, what to do next? Huh?
Multiply by 2 both sides.
Now what?
Divide by 2/3. You want to-
So why are we happy with this? Because your calculator can compute what the sine of 30 degrees is, right? If it's in angle mode, it's in degree mode. If its angle is in degree mode, it will compute the appropriate value for sine of 30 for you. So there it's approximately 35.8. So now we know what C is. What about B? How do we find B?
You can't use Pythagorean theorem.
So yeah, we know that's hypotenuse and one over there, so
Yes, you could use Pythagorean theorem since you know 2 out of the 3 legs. But let's not do that. Let's find it another way.
Cosine.
Yes, excellent. Cosine of what?
um, 30.
Yes. Which is equal to what? Always it's adjacent over hypotenuse. So it's going to be So then B is what? Which then, when you plug it into your calculator in degree mode, you get that B is approximately 31. So we found it. We found C and we found B. This is called solving a right triangle. You're given a right triangle. You're given one piece here of length, maybe 2 angles. And then you're supposed to find all of the rest of the information. I could have also not given you this angle. You could have found it by saying, oh, what's 180? So this is 60, this is 90.
150.
150, so what's 180 minus 150? 30. I could have not given that to you and asked you to find it, for example. Okay. This is a very short section. Just like 2 pages. Okay, once I'm done with this section, we'll go back to doing review problems. How about that? It's a very short section. Are you serious? It's like 2 pages. Okay. So let's do another example. You got another right triangle. So then we got A, B, and C. here's little c. Here's little a. And here's little b. Let's find out what those angles are. 32 over here, and that's 24. Or 24. Okay, find little b, little c, and capital B, because we don't know what this angle is. Let's start with capital B. How do we find that angle?
32 plus 9
Minus what?
180.
You're gonna get a negative value there.
I mean,
58 degrees.
You would have gotten the right number. It just would have had a negative on it. It's not that big a deal as long as you know this is not a negative angle. So what do you get?
88.
Is it 88 or 58?
58 degrees.
It's 58.
Yeah.
Let's see if that makes sense. 58 plus 32, that gives me 90, and 90 plus 90 is 180. Yeah, I'm gonna go with 58. Okay, so now let's do one of these guys.
Sine of 32.
Sure. Which equals what?
24 over c.
Correct. And then we could solve for little c by multiplying both sides by little c. Get this. And then you divide both sides by sine 32. This is approximately 45.29. Okay, found little c. What's a little b?
Maybe it's cosine.
Why not? Cosine of what?
33.
Equals what?
B over. Yeah, just B over 45.29.
Okay, so how do we find b?
I mean,
Right? Multiply both sides by 45.29, because then it will cancel here and show up here. And then that means b is approximately, when you plug it into your calculator, and your calculator is in degree mode, 38.41. So then you found b.
Okay, I have a question.
Yes, ma'am.
Why are we, on the last problem, we used that lower corner of 30, and now we're using the 32. Do you always use that part of the triangle for this, or can you use the other angle?
It's a great question. Actually, you can use the other angle. So let's do the whole problem using the other angle. Doesn't matter which one you pick. Do you guys have your calculators ready? You guys have recorded what we wrote already? I'm going to show you guys the angle doesn't matter. So solving it using the other angle, you use, let's say, sine of 58 degrees. But that's opposite, which is little b. Let's say we don't know it again. Over hypotenuse, little c, which we don't know it. So maybe using sine on that one isn't a good idea. Cosine of 58, though, is adjacent, or we do know it, it's 24. Over hypotenuse, we don't know it, but we can find it. Multiplying both sides by c. And then that means when you get c is equal to so let's see. What is 24 divided by cosine of 58 degrees? Say what? 25? 45.28899. So basically 45.29. Is that what we got for C last time?
Yes.
Aha. So then now that we know C, this can be found. So this is the same thing as B over 45.29. Multiply both sides by 45.29. That means B is equal to sine 58. So then that implies B is equal to what?
38.4.
78?
38.
38.
38.42.
Is that what we got last time? Okay. Does that make sense? It doesn't matter which one you pick. You just have to use sine and cosine appropriately. If you pick this one, opposite has to be B. If you pick this one, opposite has to be A. Okay. Okay, one last problem, and then we'll go back to doing the other stuff. I thought we were gonna run low on time, but no, not at all. And I don't want to jump a section too quickly. So then we could do a lot of review problems today. Does that sound fun?
Yes.
Free homework help?
Yay.
1725. This is alpha and beta. Little c. Okay. We want to find alpha, beta, and little c.
So with h squared equals 7.
Say what? Oh, okay. So little c squared is equal to 17 squared plus 25 squared, right? Which implies that c is equal to the square root of 17 squared plus 25 squared, which implies that c is equal to what? It's approximately 30.23. When you plug all that into your calculator, it outputs approximately 30.23. Okay, so we know this one. But what about alpha and beta?
Can you use the same method as last one? So for example, find the sine of beta. Over 30.
Sine of beta is equal to 17 over something.
Over 30.8.
Sine of beta,
25.
25.
30.23.
Okay. But that's sine of beta. I want to know what beta is. So what's beta? I don't like how the textbook does this, because it doesn't even define inverse trigonometric functions and what they are. So what you have to do to undo this sine, we want to know what beta is. What is beta? So to remove the sine part, you have to take the sine inverse of both sides. So then you get sine inverse of sine of beta. It just cancels the sine out and leaves beta. But the sine inverse shows up over here. But it just seems like I'm saying all this stuff for no reason. The book needs to do a better job at the logical flow of the descriptions. So basically in college algebra or pre-calculus, you guys learned that given a function f of x, there exists an inverse function, f inverse of x, such that f of f inverse of x is equal to f inverse of f of x, which equals x. Meaning if you compose the inverse function with the function in whatever order of composition, what will be inside is just what's inside the parentheses. Sine inverse is that very inverse function to sine. And you have it on your calculator that says sine inverse. You guys see it on your calculators?
Yeah.
Make sure you take a look at it and find it. Okay? Everybody should have it on a scientific calculator. Okay? So taking the sine inverse, really in your calculator, you get this value, 25 divided by 30.23, and then you say sine inverse of that value. So do it. What do you get? That's what beta is.
$55.79.
55.79, which is approximately 55.8. Does everybody get that? Does everybody get that? I mean, do you get that in your calculator? It's dead?
Yeah. I don't have a charger for it.
Okay.
I gotta order a new one.
That's what I got.
You got that? Okay. Really, it's just putting this expression into your sine inverse, and you get the output of that. It's getting to that point that is the real math. The real math is getting to that point. So now that we know beta, how do we find alpha? Because we're done if we find alpha now.
So 55.8 plus 90.
Right? So this implies that your alpha is what? Did you guys get 34.2?
Yes.
That makes sense because if I add 34.2 to 55.8, that's 90. Any questions about this? Okay, now I'm back to doing that problem from 2.1. What did it say again? Sine squared alpha tangent squared beta minus cosine squared beta. So that it equals 1. So, oh, and alpha and beta were complementary. So alpha and beta complementary means alpha plus beta is equal to what? 90. So this means beta is equal to 90 degrees minus alpha. Keep that in mind. So we'll rewrite what we have here. We're trying to show that this equals 1. This is begging us to utilize the cofunction identities. So cofunction of tangent is cotangent, meaning cotangent of beta is the same thing as tangent of 90 degrees minus beta. Right? So that means that the tangent of beta is the cotangent of 90 degrees minus beta. So that means when I see a tangent beta, I could replace it with the cotangent of 90 degrees minus beta. Or if I see a cotangent beta, I could replace it with the tangent of 90 degrees minus beta. But what is 90 degrees minus beta the same as? If this is true, 90 degrees minus beta is the same thing as alpha. Ding, 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 ding. That's what I wanted to happen. That was the connection I was hoping to get at earlier. That this is alpha. So this means, for example, that tangent of beta is equal to the cotangent of this, but that's really cotangent alpha. That was the key. So let's rewrite this. This means we got sine squared alpha cotangent squared alpha minus cosine squared beta. Now that things are moving more towards alpha, let's just convert that cosine squared beta. What is cosine squared beta? Or namely, what is cosine of beta? The same thing as sine of what? Cofunction identity. Cotangent beta is the tangent of 90 degrees minus beta. Tangent of beta is a cotangent of 90 degrees minus beta. Cosine of beta is the same thing as sine of
90 minus beta.
Yeah. Good. Oh, but 90 minus beta is the same thing as what? Yes. So let's rewrite this, everything in terms of alpha. Cosine squared beta, which is this, if you squared it, it's sine squared alpha. Because this is cosine squared beta. So when I square this, I get sine squared alpha. Okay? So notice when I factor out a sine squared alpha, we get cotangent squared alpha minus 1. But what is cotangent squared alpha minus 1? Go back to 1.4. 1 plus cotangent squared is equal to cosecant squared. And cosecant squared is the same thing as what? Yes. Yes. So, what now? Because we have cotangent squared alpha minus 1. That means over here, which one of these relations could we utilize? Or if you don't want to go down that route, we have this. But again, if you distribute that, you're going to get cosine squared alpha minus sine squared alpha, which again doesn't reduce to 1. So, no suggestions on how to do it? Does anyone have any idea at all? What about the Pythagorean identity sine squared alpha plus cosine squared alpha? If we could somehow get this to reduce to sine squared alpha plus cosine squared alpha, or sine squared beta plus cosine squared beta, then we'd be done. Another neat trick in solving these problems is, if you guys are stuck, you're saying, I want to show that this is true, right? So what is a different kind of form of that I could show is true? If you show sine squared alpha tangent squared beta is equal to 1 plus cosine squared beta, you'd be done as well. Hmm?
I thought about doing
You
that.
thought about doing that? Okay. But notice that, for instance, switching tangent squared beta would be like cotangent squared beta. Did I say cotangent squared beta? I meant cotangent squared alpha, because alpha is 90 degrees minus beta. So you could switch it to this. If you could show this is true, you'd be done. But this is the same thing as sine squared alpha times cosine squared alpha divided by sine squared alpha. Cancel that. That would mean that it reduces to showing that cosine squared alpha is the same thing as 1 plus cosine squared beta. So if we could show cosine squared alpha is the same thing as 1 plus cosine squared beta, we'd be done.
Is
Again,
cosine squared beta the same as sine of alpha?
good. So let me write a box here. So you're saying 1 plus cosine squared beta is the same thing as 1 plus, what are you going to say?
Sine squared alpha?
So cosine of beta is the same thing as sine of 90 degrees minus beta. But that's the same thing as sine alpha, right?
Yeah.
Is this what you're saying?
Yes.
So that means cosine of beta is the same thing as sine of alpha. So this is the same thing as 1 plus sine squared alpha. Is that what you were saying?
Mm-hmm.
Okay. So if we could show cosine of alpha is equal to 1 plus sine squared alpha. But that won't mean, hold up. This would imply cosine squared alpha is equal to 1 plus sine squared alpha. But that's not true, because cosine squared alpha minus sine squared alpha is equal to 1, is not equal to 1. Something's weird with this problem. I can see why you're stuck. I'll get back to you guys on Thursday about this one. Sometimes I just assign problems randomly. Very rarely, very, very rarely, problems are incorrect in here. Very rarely. It doesn't happen often. But maybe when it says given alpha and beta are complementary, verify the following equations are identities. But notice when we break it down, we're getting that cosine of alpha minus sine of alpha equals 1, but that's not true. So I'll have to get back to you guys on this problem. If it has an intrinsic inconsistency in it, I won't assign it. I'll just give you full credit for that one.
It just seemed like no matter what I did, I just wasn't getting anything.
Yeah. Let's put that to the side for now. Don't worry about this problem right now. Ask about other problems for your homework. because this isn't true. Cosine squared alpha minus sine squared alpha does not equal 1. And that's what this is implying whenever you use the cofunction identities. So don't worry about that problem. Which one?
No, that's 2.1.
The number 18 and 1.4.
Yes. This is very rare. I've taught out of this book several times. I don't like the logical flow of the book, how it's presented, but typically it's not filled with errors. So I'm a bit surprised here. What number did you guys say? 18 and 2.1?
1.4.
Oh, 1.4. $18. Cotangent of theta times tangent theta plus cotangent theta and this ends up equaling cosecant squared. Are we supposed to prove this? Prove. Okay. So we'll start off on the left-hand side. Okay. So then we're just going to multiply through this cotangent of theta. So this becomes cotangent tangent theta plus cotangent squared theta, right? We want to find out that it ends up equaling a cosecant theta, and that's a 1 over sine of theta squared, that is. So breaking down cotangent and tangent into the fundamental sine and cosine identities, we get that this is cosine of theta over sine of theta multiplied times sine of theta over cosine of theta plus cosine squared theta over sine squared theta. We notice here that these cancel. So that ends up equaling a 1. And that's what we get there. But notice that this is divided by 1, and we can multiply top and bottom by sine squared. Here, sine squared, you get a common denominator. Combining them all under the same divisor, you get this. But the numerator is what? This thing is the same as what? 1 by the Pythagorean identity. So you get it's 1 over sine squared theta. Now what? You're done.
Yeah, because 1 over that is close.
That's correct. That last problem is quite weird. It's saying sine squared alpha minus cosine squared alpha is equal to 1. I would not put something like that on. Yes, ma'am.
I just had a question. Before our first test, will we get our homework back to like review?
Yes.
Okay.
Mhm. And I'll upload solutions on the problems. So how to do the problems.
Oh,
How to do all your homework problems. I'll upload solutions on that.
okay.
Yeah, when is it?
Once we're done with chapter 2. Which chapter 2 has sections all the way to 2.4. And we'll have a day of review as well. We'll have a day where all we do is review. What other problems? So this one's done. Give me more, give me more. Okay, I'm not gonna flip, just tell me what does it say? What does it say? What does it say?
And write the given function pattern in terms of second function indicator. For two, it says tangent data in terms of secant data.
So it just says get tangent of theta? Write it in terms of secant?
Yeah.
Okay. So recall secant is what? Okay. Tangent is what? Okay. So to do this, we can use one of those fundamental identities as well. Wait. Tangent squared theta plus 1. Okay. So we want to write tangent all in terms of secant, right? So notice that we could just start from here. Solve for tangent. Subtracting the 1 from both sides. Right? And then take the square root of both. So you get tangent of theta is equal to plus or minus the square root of secant squared theta minus 1. Plus or minus. And there you have it. That's tangent purely in terms of secant. Notice if you try to do it like this, just using tangent right here, 1 over cosine is embedded in the definition of tangent. And you could have said that this is secant theta sine theta. Secant theta sine theta is tangent theta. But it implores us to represent tangent purely in terms of secant. This is tangent in terms of secant and sine. So this is why doing it like this is not correct. Because it needs it purely in terms of secant. And that's why this is correct. Because this is purely in terms of secant. That's what tangent is, purely in terms of secant. Here, it's got a sine in it. It kind of ruins it. Make sense? Okay. Give me some more. Give me some more.
63.
What does it say?
It's on section 2.1.
What does it say?
I don't have my book, so.
Oh, so what?
I just remember I was stumped.
2.1, which number?
63.
63. Oh, the diagonal of a cube. I think about cubes every single day. I'm trying to invent a theory of quantum gravity, and it is a major part of my theory that space and time can be quantized in terms of cubes of Planck volume. So you got a cube, it's 10 by 10 by 10. What it wants to know I'm doing this because I have to. There you go. So the dotted stuff is like in the background, where the solid stuff is in the foreground. Does that make sense? So you have a cube, it's 10 by 10 by 10, and you aspire to find what is this value from here, or for, let's say, from here all the way to right there, the diagonal of the cube, right? So you can break that up into a two-part problem. Notice it forms a right triangle, right? If we take this piece out, you get something like this. Okay, where the white value is 10 for sure, but this and that is unknown. Our final answer we want to know is this, diagonal 2. This is diagonal 1. The one that's on the ground is diagonal 1. The one that's slanted that goes all the way to the top corner, that's what we're going to call diagonal 2. Okay? So taking this part of the cube, taking that part, it's a square, right? So this is what we have. This is 10 by 10, and this is diagonal 1. This is at the base of the cube. So we can find diagonal 1 using what? Because this forms a right triangle.
D1 squared is equal to 10 squared.
Correct. D1 squared is equal to 10 squared plus 10 squared by the Pythagorean theorem. So that means D1 is equal to which that means that's equal to 10 root 2. Because the square root distributes to both. And the square root of 10 squared is just 10. Okay, so now we know D1, it's 10 root 2. Oh, and now we know this leg and this leg, we can find D2.
What formula are we using?
This one right here? Or you mean
Yeah.
the next step?
No, yeah.
This one?
Yeah.
This is the Pythagorean theorem applied to this right triangle right here, here to here. I created this whole thing because this is supposed to represent the base of the cube. This whole thing is the base of the cube. Base of the box. It correlates to the shaded region right here.
So if we're solving for one triangle, why are we using 10 squared?
Because the Pythagorean theorem says that if this is A, this is B, and D1 is like your C, A squared plus B squared is equal to C squared. That's okay. Good question. And so then when you take the square root of both sides, you get D1 is equal to the square root of 10 squared plus 10 squared, which I just said that's just 2 10 squared. And then you take the square root, you distribute the square root to both of them. So you get 10 root 2 as your D1. So that's why we have this like this. But we want to know what is the diagonal of the cube, not what is the diagonal of the base of the cube. So we also need to calculate this length. But we couldn't have done it before because we didn't know what the diagonal of the base of the cube was. But now we can. So what is D2? It's another application of the Pythagorean theorem.
D2 squared equals to 10 squared.
That implies D2 is equal to the square root of 10 squared plus 2 times 10 squared, which that's just 3 10 squared, which then that's just the same thing as 10 root 3. And this is your D2, and this is your final answer. It's 10 root 3.
If in the first part, why is it 2 times 10 squared? I thought it was.
Oh, it is root 2, yes. Correct. Let me go back there. 10 square root of 2, not just 2. 10 square root of 2. Oh, yes. But when you square it, this 2 goes away, right? Notice that, let me create some more room. I actually didn't mess up. But I did go really quickly, which might make you lose where I'm at. When you square this, that's the same thing as square root of 2 squared times 10 squared, which is the same thing as 2 times 10 squared. So that's why I had a 2 times 10 squared here. So then the steps, again, it's what I erased. This becomes 3 times 10 squared. Square root, this becomes square root of 3, square root of 10 squared. But then that just becomes 10 square root of 3. And that's your D2.
Wait, why did it become 3?
Why did it become 3?
Yeah. Why did it go from 2 to 3?
Oh, here, from here to here? Aha, because 10 squared plus 2 10 squared is 3 10 squared. Just like x squared plus 2x squared, what does this equal, young lady? Yeah. So the x squared is like playing the role of 10 squared. But when it's an x, you're just like, oh yeah. But now when it becomes a 10, it's unfamiliar. But it still follows the same rules, right? Okay. So the diagonal of the cube is 10 root 3, which makes a lot of sense. If we had a unit cube, the diagonal would have been square root of 3. But we have a 10 cube, so the diagonal is multiplied by a factor of 10. Say what? Are you going to be getting a lot of cubes? Oh, because I like cubes so much? Maybe, who knows? Say what? Oh, please don't. You do know when a student begs in fear to not do it, you're like, yeah, you're like inclining the professor to do it. Yes, ma'am.
I kind of have a question, but on the last.
There's no such thing as that. Don't ever say that again. Did you guys hear what she said? Yes, that's what she said. There's no such thing as a dumb question. And here's why. If you are questioning, that implies that you have curiosity. If you have curiosity, that is the definition of intellect. So the fact that you have a question implies that you cannot be dumb. So dumb question is an oxymoron.
So on the 10 squared plus 2 times 10 squared, if we didn't know like the whole 3 times 10 squared thing, would we still got the same answer?
Yeah, you would have just gotten a decimal. So you could have done all this stuff and gotten a decimal. Mathematicians just like to work with exact results.
So we would have still got the same thing even though we didn't know the whole like.
Yes, I would prefer this. But if you got a decimal, I would check to see if it equals 10 root 3. And if it did, then you get full credit. What are the questions? Absolutely. Give me more. Give me more. I want to solve all the questions you have. I want to do your whole homework for you. I want to do all your homework for you. Give me all the problems. Yeah, what is it?
Negative 11 over 2.
Cotangent of
With theta is 0.4.
So what is it asking you to do? find all the other trig functions. Super easy. So here's quadrant 4, right? That's where theta is, right?
Yeah.
Okay. So cotangent is this, but cotangent is the same thing as what?
That's close.
Or you could say it's, yeah, 1 over tangent. Okay. It's the same thing. But let's use this expression. Okay. So remember tangent was opposite over adjacent, right? So cotangent is going to be what? Excellent. So negative 11 over 2 is the same thing as adjacent over opposite of our theta in quadrant 4. Okay. So adjacent is going to be our 2, or our 11, and our negative 2 is going to be down here. Notice that negative can be up here or it could be down here based on geometrical significance. Meaning, oh, it's in quadrant 4, the y is what has to be negative, not the x, right? The y is, that's why I put the negative 2 on the y, because that's what's negative here, not the x. So now, based off of this, if we can solve for hypotenuse, we can figure out all the rest of the trigonometric functions. So what is the hypotenuse? So hypotenuse is equal to 121 plus 4, which is equal to the square root of 125, which is equal to the square root of, that's 5/4. And that's the same thing as square root of 25, square root of 5. And that's the same thing as 5 square root of 5, hypotenuse. So then let's start to do all the trigonometric functions. Sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. Cotangent was given. Secant is then this. And cosecant is this. Any questions on how I set that up? No questions? Okay, what else? Got 3 minutes left. Give me some. Give me a question. I'm trying to do your homework for you.
Can we do 42 on 2.1?
Yeah, what does it say?
Cosecant of 6x minus 3.
cosecant of 6x minus 2.
And then secant of 2x plus 5.
Are they multiplied together? What page is it on? 52?
Yeah.
What number?
I think it's at 42.
Yeah, 52 should be at 42.
42? Oh, yeah.
And it's a 3 instead of a 2.
Okay. Thank you, sir. And then it says comma.
Secant of 2x plus 5.
So what does it want with these?
Divided that to make it equal.
Ah, so we set them equal. Okay, so then let's represent cosecant and secant as what they really are. Okay, that's what they really are. So it says find the value of x that would make them equal. So guess what? We're going to set them equal to each other and try and find the x that satisfies that. Notice when you cross multiply, what you get is cosine of 2x plus 5 is equal to sine of 6x minus 3. So, what can you do now? No, because the trigonometric functions are surrounding it. And you can't take the cosine inverse or the sine inverse because one of them would remain. So, what do? You say that this is some theta, is it not? So you create a triangle out of it. So cosine of theta. Okay. And this, that's also an angle. This 2x plus 5 is an angle, and that 6x minus 3 is an angle. So let's say cosine of 2x plus 5 is the same thing as cosine of theta, where theta equals 2x plus 5. All right. And then we could say, okay, let's say that cosine of theta is some x over h, like usual, where this is x, this is y, this is h. Oh, and let's not use x. Not that kind of x. Let's use a capital X to avoid confusion. All right? So that means sine of theta is y over h. But 6x minus 3 and 2x plus 5 are not the same. It's just that cosine of 2x plus 5 and sine of 6x minus 3 evaluate out to be the same value. Right? There's many ways you can do this. You can set up a triangle and say that theta, this is a 2x plus 5. And so cosine of theta is like cosine of 2x plus 5 is equal to that. But we don't know y and we don't know h. Sine of theta would also be represented like this. we don't know y, and we don't know h. Another way you can look at it is that for what angle is a sine and the cosine equal to each other?
I use a cofunction. I don't even know how.
That's fine. So cosine of 2x plus 5 is the same thing as sine of what? That's perfectly fine. And call this degrees, right? They're degrees. It's implied that they're degrees. The book even has a degree on them. Yeah. Okay. So then that means this is the same thing as sine of 90 degrees when we distribute that negative. So this is the same thing as sine of 85 minus 2x. Okay.
I use the cosecant theta equals to secant 90 minus theta. That's what I use.
So then the cosecant of 6x minus 3 is equal to the secant of 90 degrees minus 6x minus 3. Yeah, that was an accurate statement in terms of utilizing the cofunction. So how do you find x?
I took 90 minus 6x minus 3 equals to 2x plus 5.
How does that equal 2x plus 5?
Because the secant, the angle is 2x plus 5. And if it's equal to it, I guess I would say that. Because I got the angles I got. It came out like the math was right, but I don't know if I did the.
When is this class over?
10:40.
Oh, we're like 5 to 6 minutes over.
I'm learning.
That's good. We will continue.